Tonight, we're going to explore something that sounds like a mistake. Not Mars, not the distant outer planets, not some theoretical object billions of light years away. We're going to talk about going to Venus, the planet that is, right now, closer to Earth than any other planet in the solar system. The planet that is almost exactly the same size as Earth. The planet with nearly the same gravity, nearly the same mass, the same rocky composition. The planet that formed from the same cloud of gas and dust as Earth, at nearly the same time, in the same neighborhood of the solar system. The planet that, for the first billion years of its existence, may have had liquid oceans and a climate that would not have seemed out of place on our own world. Why anyone who lands on the surface of Venus would not survive long enough for the question of coming back to even be relevant. Why the physics and chemistry and geology of Venus have conspired to produce a world that is, despite its proximity and its similarity in size and composition, the most catastrophically hostile planetary environment in the solar system short of the Sun itself. Why every spacecraft ever sent to Venus's surface has been destroyed within hours. Why the 127-minute survival record set by a Soviet probe in 1982 represents the absolute limit of what our engineering has ever achieved on that world. And why a suited human on Venus's surface would survive not for minutes, but for seconds. But here is where this story becomes extraordinary. Because hidden inside the nightmare of Venus's surface, at an altitude of 50 kilometers above it, there exists a layer of the Venusian atmosphere where conditions are the most Earth-like of any environment outside of Earth itself. A band of sky where the temperature is between 0 and 50 degrees Celsius, where the atmospheric pressure is similar to what you feel at the base of a mountain on Earth, where solar radiation arrives at roughly the same intensity as a cloudy day at Earth's surface, where, in principle, a structure filled with ordinary breathable air would float naturally in the denser surrounding atmosphere, without any additional lift system. A place where scientists have seriously proposed building a city, a floating habitat that would drift around Venus in the permanent hurricane-force winds at that altitude, never landing, never trying to land, circling the planet continuously in a band of sky that represents the one zone where the laws of physics are, grudgingly, willing to discuss the possibility of human presence. And so tonight's story has two halves. The first half is the systematic destruction of every assumption that makes Venus seem like it should be approachable. The second half is the extraordinary discovery that makes scientists, real scientists, employed at real space agencies with real mission proposals in formal review, argue that Venus may in some respects be a better candidate for human presence than Mars. Not on its surface. Never on its surface. But in its sky. By the end of tonight, you're going to understand why Venus is hotter than Mercury, despite being twice as far from the Sun. Why the clouds that cover Venus are made of concentrated sulfuric acid. Why the atmospheric pressure at Venus's surface is equivalent to being 900 meters underwater in Earth's oceans. Why the Soviet Union's Venera program, the most successful Venus surface mission program in history, could never keep a probe alive for more than 2 hours and 7 minutes. Why any suit capable of protecting a human at Venus's surface would weigh so much and be so rigid that it would be effectively impossible to work in. Why the fuel mathematics of launching from Venus's surface are worse than launching from Earth's surface, despite Venus's slightly lower gravity. And why, 50 kilometers up, everything changes. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about what you know about Venus. Most people know it as the second planet from the Sun, the brightest object in the night sky, after the Moon. Visible in the west just after sunset, or in the east just before sunrise, sometimes called the evening star or the morning star. Most people know it is roughly similar in size to Earth. And most people, if they think about destinations for human exploration of the solar system, think of Mars first and give no particular thought to Venus, treating it as either a stepping stone or an irrelevance. The scientists who study Venus have spent decades arguing that this dismissal is wrong. And when you look at the raw comparative data between Venus and Mars as potential human destinations, the scientists have a point that is difficult to argue with, at least on the surface level statistics. Venus has a diameter of 12,104 kilometers. Earth's diameter is 12,742 kilometers. Venus is 95% of Earth's diameter. Mars, by contrast, has a diameter of 6,779 kilometers, barely half of Earth's. In terms of size, Venus is essentially Earth's twin. Mars is a smaller, thinner world. Venus has a mass of approximately 4.87 times 10 to the 24th kilograms. Earth's mass is 5.97 times 10 to the 24th kilograms. Venus is about 81.5% of Earth's mass. Mars has a mass of only 6.39 times 10 to the 23rd kilograms, barely 10.7% of Earth's mass. Venus is nearly 8 times more massive than Mars. In terms of planetary substance, Venus is vastly more similar to Earth. The surface gravity of Venus is 8.87 meters per second squared. Earth's is 9.81 meters per second squared. Venus has 90.5% of Earth's surface gravity. Your body would feel nearly identical on Venus to how it feels on Earth. You would weigh about 10% less. Mars has a surface gravity of only 3.72 meters per second squared, 38% of Earth's. On Mars, you weigh less than half what you do on Earth, and the long-term effects of living in that reduced gravity are among the most serious health concerns for any Martian settlement. Venus does not have this problem. Venus is at an average distance from the Sun of 108 million kilometers. Earth is at 150 million kilometers. Mars is at 228 million kilometers. Venus is closer to the Sun, yes, but the critical distance for a human mission is not the distance from the Sun, but the distance from Earth. At its closest approach to Earth, called inferior conjunction, Venus is approximately 38 million kilometers away. Mars, at its closest approach, called opposition, is approximately 55 million kilometers away. Venus is 45% closer to Earth at its nearest point. And even at its farthest, Venus is only about 257 million kilometers from Earth, compared to Mars's maximum distance of about 401 million kilometers. At every point in their respective orbits, Venus is closer to Earth than Mars. The travel time to Venus is shorter. Using a Hohmann transfer orbit, the minimum energy trajectory between Earth and Venus, the trip takes approximately 3 to 5 months. The equivalent trip to Mars takes 6 to 9 months. Venus missions are shorter in transit time by a factor of roughly 2. Astronauts going to Venus spend less time in microgravity during transit. They are exposed to cosmic radiation in deep space for less time. They consume fewer resources in transit. Everything about the journey to Venus, compared to the journey to Mars, looks more manageable. And Venus has no months-long wait for a return launch window baked into the mission profile the way Mars does. The orbital geometry of Mars missions forces any crewed expedition to stay on the Martian surface for roughly 2 years, waiting for the next return launch window. This is an inescapable feature of the orbital mechanics. For Venus missions, the geometry is different, and the wait at Venus for a crewed expedition at the cloud level would be approximately 16 months from one launch window to the next. Still a long time, but shorter than the Martian wait. So Venus is closer, faster to reach, has nearly Earth-normal gravity, is similar in size, has a shorter wait for the return window. On every metric of accessibility, Venus beats Mars. And yet, when space agencies and private companies and enthusiastic futurists talk about where humans will go next in the solar system, they universally say Mars. Venus is almost never mentioned seriously as a near-term human destination. There is a reason for that. Many reasons, in fact. And every single one of them breaks your intuition about what a planet similar in size to Earth could possibly be like. Let us begin with temperature, because temperature is where Venus first announces that it is not what its surface statistics suggest. The average surface temperature of Venus is 465 degrees Celsius. That is 869 degrees Fahrenheit. For comparison, the melting point of lead is 327 degrees Celsius. The melting point of zinc is 419 degrees Celsius. The melting point of tin is 232 degrees Celsius. At Venus's average surface temperature, lead is liquid, zinc is liquid. Tin has been liquid for over 200 degrees. The surface of Venus is hot enough to melt most metals that humans commonly work with. The surface temperature of Venus is roughly uniform across the entire planet. It does not vary significantly between the poles and the equator. It does not vary significantly between the day side and the night side, despite the fact that a Venerian day, meaning one complete rotation of Venus on its axis, lasts 243 Earth days. The planet rotates so slowly that you might expect the night side to cool dramatically during those 243 days of darkness. It does not. The thick atmosphere distributes heat so efficiently around the planet that the temperature difference between the day side and the night side is only about 5 degrees Celsius. Venus is a uniform furnace. This is deeply counterintuitive. Mercury, the innermost planet, is far closer to the Sun than Venus. Mercury has a surface temperature on its day side of approximately 430 degrees Celsius, slightly cooler than Venus, despite receiving nearly 6 times more solar energy per unit area. Mercury's night side drops to minus 180 degrees Celsius, because Mercury has essentially no atmosphere to retain heat. Venus has more solar energy arriving at its cloud tops than Mercury receives, but less of it penetrates to the surface. And yet Venus is hotter. The mechanism responsible for this is the runaway greenhouse effect, and it is one of the most important processes in planetary science because it is not merely a Venusian curiosity. It is a warning about what happens to a planet similar in composition to Earth when atmospheric chemistry goes wrong. Venus's atmosphere is approximately 96.5% carbon dioxide, with roughly 3.5% nitrogen and trace amounts of other gases, including sulfur dioxide. Carbon dioxide is a greenhouse gas. It allows visible light and ultraviolet radiation from the sun to penetrate and warm the surface, but it absorbs and re-emits the infrared radiation that the warm surface tries to radiate back into space. The more CO2 in the atmosphere, the more heat is trapped. Earth has a CO2 concentration in its atmosphere of approximately 0.04%. Venus has a CO2 concentration of 96.5%. The difference in greenhouse warming between these two concentrations is not proportional to the difference in concentration. It is catastrophic. The process that produced Venus's current state began in the planet's early history. In Venus's youth, there is strong evidence that it was a much more temperate world. The planet may have had liquid water oceans for roughly 2 to 3 billion years. The Sun was cooler in the early solar system, and Venus, at a somewhat greater distance from the Sun than today, due to orbital drift over billions of years, may have been within or near the habitable zone. Water, present as oceans, would have dissolved CO2 from the atmosphere and locked it in carbonate rocks, the same process that has kept Earth's temperature stable over billions of years. But as the Sun brightened over geological time, Venus began to warm. The warming caused more water to evaporate from the oceans. Water vapor is also a greenhouse gas. The increased water vapor caused more warming, which caused more evaporation, which caused more warming. This is a positive feedback loop, and once it begins, it does not stop. The runaway greenhouse effect took hold. The oceans boiled away over millions of years. The water vapor in the upper atmosphere was broken down by solar ultraviolet radiation into hydrogen and oxygen. The hydrogen, being light, escaped to space. The oxygen reacted with surface rocks. The water was gone. Permanently. The CO2 that had been safely locked in carbonate rocks was baked out of them by the increasing temperature and released into the atmosphere. Venus became what it is today. The second critical number is atmospheric pressure. The pressure at Venus's surface is 92 bars, where 1 bar is approximately the atmospheric pressure at Earth's sea level. 92 bars is approximately the pressure you would experience at a depth of 900 meters in Earth's ocean. This pressure is not merely uncomfortable. It is structurally dangerous to any vehicle not specifically engineered to withstand it. Submarines are designed to operate at pressures of this magnitude, and they are heavily reinforced pressure vessels made of thick steel. A spacecraft designed for space operations, optimized for low mass and ease of construction, in vacuum or at Earth's atmospheric pressure, would be crushed by Venus's surface pressure the way a plastic cup is crushed underwater when you push it down far enough. The combination of 465 degrees Celsius and 92 bars of CO2-rich atmosphere is what killed every probe the Soviet Union ever sent to Venus's surface. Killed them within hours, despite being specifically and carefully designed to survive as long as possible. The Venera probes were spherical pressure vessels, heavily armored, built like small tanks, designed by some of the best aerospace engineers of the 20th century with the explicit goal of surviving on Venus. The best they ever achieved was 127 minutes. This is not a failure of engineering ingenuity. It is an honest assessment of what the environment requires. Before we reach the surface, we need to understand something about Venus that contributes to its extreme conditions, and that is completely anomalous compared to every other planet in the solar system. Venus rotates in the opposite direction from Earth, and from every other planet except Uranus. If you were standing on the surface of Venus and could somehow see the Sun through the perpetual cloud cover, the Sun would rise in the west and set in the east. This retrograde rotation is unexplained. The leading hypothesis is a massive impact early in Venus's history that reversed its original rotation direction. But this has not been confirmed. Venus also rotates extraordinarily slowly. One Venusian sidereal day, meaning one complete rotation of Venus on its axis relative to the distant stars, takes 243 Earth days. Venus's year, the time it takes to orbit the Sun, is 224.7 Earth days. This means Venus's day is longer than its year. It rotates slower than it orbits. The length of a solar day on Venus, the time from one sunrise to the next due to the combined effect of rotation and orbital motion, is approximately 116.75 Earth days. You would wait 116.75 Earth days, about 4 months, between consecutive sunrises at any fixed point on Venus's surface. This extraordinarily slow rotation has several important implications for any human mission. First, it means there is no practical way to use solar power on Venus's surface. The night side of Venus is in darkness for more than 58 Earth days between sunsets and sunrises. No battery system of any conceivable practical size could store enough energy to power a surface habitat through 58 days of darkness. Nuclear power would be required for any surface installation. Second, it contributes to the uniform temperature distribution across the surface. The slow rotation means any point on the surface experiences extremely long days and nights, but because the thick atmosphere distributes heat globally, the temperature variation is minimal. A planetary surface that should, based on day length alone, show dramatic temperature swings between day and night, instead shows a near constant temperature because the atmosphere has far more thermal inertia than the surface rocks. Third, and perhaps most counterintuitively, Venus's slow rotation means it has, essentially, no global magnetic field. Earth's magnetic field is generated by the circulation of molten iron in its outer core, and this circulation is driven partly by the Coriolis effect of Earth's rotation. Venus has a similar iron core, but its slow rotation produces almost no Coriolis effect, which means the core's convection does not generate a significant dynamo, which means there is no global magnetic field. A weak induced magnetic field exists from the interaction of the solar wind with the Venusian ionosphere, but it is far weaker than Earth's field. The magnetic field of Earth is the primary shield protecting life from cosmic radiation and from the high-energy particle streams in the solar wind. Without a magnetic field, the surface of a planet is exposed to significantly elevated radiation levels. However, Venus's thick atmosphere provides an alternative form of shielding. The column of atmosphere above the surface of Venus, 92 bars worth of CO2 and nitrogen, provides radiation shielding roughly equivalent to several meters of water. Any charged particle or high-energy photon penetrating to Venus's surface has to pass through 90 atmospheres of dense gas, which attenuates the radiation significantly. Counterintuitively, the surface of Venus may actually have lower radiation levels than the surface of Mars, which has a thin atmosphere and no global magnetic field, and is therefore exposed to cosmic radiation from above, with minimal shielding. This fact about radiation will become critically important when we reach the cloud level section later. For now, simply note that the absence of a magnetic field, which sounds like a catastrophic problem, is actually less dangerous on Venus than on Mars due to the compensating effect of the dense atmosphere. Let us spend more time with the Venusian atmosphere, because it is not simply a scaled-up version of Earth's or Mars's. It is qualitatively different in ways that compound the surface mission challenge at every step. The total mass of Venus's atmosphere is approximately 4.77 times 10 to the 20th kilograms. Earth's atmosphere has a mass of approximately 5.15 times 10 to the 18th kilograms. Venus's atmosphere is approximately 93 times more massive than Earth's entire atmosphere. The Venusian atmosphere contains more mass than Earth's entire ocean. When you are on the surface of Venus, the weight of the atmosphere pressing down on you is equivalent to the weight of a column of Earth's ocean nearly a kilometer deep, pressing on every square centimeter of your body. This has immediate practical consequences for any spacecraft attempting to land on or launch from Venus's surface. Let us begin with landing, because landing is where you encounter the Venusian atmosphere for the first time. A spacecraft approaching Venus must enter the atmosphere at hypersonic speed. The entry velocity for a trajectory arriving from Earth is typically around 11 to 12 kilometers per second. At this speed, the kinetic energy of the spacecraft must be converted to heat by atmospheric friction, and the heat shield must protect the spacecraft from temperatures that can exceed 2,000 degrees Celsius during entry. This part of the process is similar to re-entering Earth's atmosphere or entering Mars's atmosphere, and it is manageable with existing heat shield technology. Below the clouds, around 45 kilometers altitude, the atmosphere becomes dense enough that aerodynamic braking becomes significant. At 40 kilometers, the atmosphere is so dense that parachutes, if deployed, would do more harm than good by catching the dense gas and creating structural loads that could damage the spacecraft. From about 30 kilometers down to the surface, the atmosphere is so thick that the spacecraft falls relatively slowly simply due to aerodynamic drag, even without parachutes. The atmosphere itself acts as a decelerator. But here is where the first problem emerges. The Soviet Venera probes took approximately 53 minutes to fall from the cloud tops to the surface. During those 53 minutes, the probe was gradually heating and being compressed as the atmospheric pressure increased from manageable levels in the clouds to 92 bars at the surface. Every minute of descent, the environment outside became hotter and more pressurized. By the time the probe reached the surface, it was already operating in an environment that would destroy it within hours, regardless of how well it was built. A crewed vehicle would face an additional challenge that the Venera probes did not: the crew inside. A probe does not care about the temperature inside, as long as its instruments remain within operating range. A human crew needs the interior of the landing vehicle to remain at a habitable temperature throughout the 53-minute descent and for the duration of the surface stay. The heat input from the 465-degree exterior environment passes through any thermal insulation at a rate determined by the insulation thickness, the thermal conductivity of the insulation material, and the temperature differential. At a 400-degree temperature differential between inside and outside, even extraordinary insulation would allow significant heat flow. Maintaining a livable interior temperature on the surface of Venus requires active cooling, which requires power, which must be generated somehow in an environment where solar panels are useless. The Venera probes addressed this partly by using the thermal mass of the probe itself as a heat sink. The probe would absorb heat during its mission, slowly warming up, and would die when the interior temperature exceeded the operating range of the electronics. Designing a system that could maintain human habitable temperatures for more than a few hours would require a continuous active cooling system of extraordinary capacity, rejecting enormous amounts of heat into an environment that is already at 465 degrees Celsius. The thermodynamic challenge is severe. You cannot reject heat into a 465-degree environment using any conventional cooling system designed for use on Earth. We have been talking about the surface conditions, but between the spacecraft entering the Venusian atmosphere and reaching the surface, there is a middle layer that presents its own specific and severe challenge: the cloud layers. And the clouds of Venus are not like any cloud you have ever seen or imagined. Earth's clouds are made of water droplets or ice crystals. They are, from a chemistry standpoint, benign. You can stand in a cloud, as you do in fog, without any ill effect on your body or your equipment. Venusian clouds are made of sulfuric acid, not dilute sulfuric acid, not the acid rain that falls on Earth's industrial regions, but concentrated sulfuric acid at a concentration of approximately 75 to 96% by weight, depending on altitude within the cloud layer. Concentrated sulfuric acid at 75 to 96% concentration is one of the most corrosive substances encountered in industrial chemistry on Earth. It is the acid used in car batteries at about 35% concentration. At 96% concentration, it reacts violently with water, with organic compounds, with most metals, with most polymers, with essentially everything except a short list of specifically acid-resistant materials. Contact with 96% sulfuric acid causes severe chemical burns within seconds. Immersion in it would dissolve organic tissue, including human tissue, with extraordinary rapidity. The cloud layers of Venus extend from approximately 45 to 70 kilometers altitude. The main dense cloud deck is between 48 and 60 kilometers. These clouds are not thin, wispy cirrus clouds. They are a thick, dense, globally continuous layer that completely obscures the surface from any view from above and completely obscures the sky from any view from below. No natural light from the sun penetrates as direct sunlight to the Venusian surface. The surface is lit only by diffuse scattered light that has filtered through 70 kilometers of sulfuric acid clouds. The light that reaches the surface is dim and has an orange-yellow color due to the scattering characteristics of the cloud particles. For any spacecraft descending through the cloud layers, the sulfuric acid aerosol poses a corrosion challenge. The droplets are small enough to penetrate small gaps in seals and connections. The acid reacts with most metals to produce hydrogen gas and metal sulfate salts, corroding the metal in the process. Aluminum reacts with sulfuric acid. Iron reacts with sulfuric acid. Even titanium, one of the most acid-resistant structural metals available, is attacked by concentrated sulfuric acid at elevated temperatures. The combination of concentrated acid and the elevated temperature of the cloud layers, which are at approximately 60 to 80 degrees Celsius in the mid-clouds, creates an aggressive corrosion environment for any spacecraft material. The Venera probes were designed with careful attention to materials selection to resist the cloud chemistry. But even so, the probes showed chemical corrosion effects after passing through the clouds. A crewed vehicle would need to pass through the cloud layer during descent and would remain below the cloud layer throughout any surface mission. If the vehicle developed any leak in its pressure seals, sulfuric acid vapor would infiltrate the interior. The concentration of sulfuric acid vapor in Venus's lower atmosphere, below the cloud deck, is low enough that it would not immediately destroy equipment. But it is corrosive enough to cause damage over time and would present a respiratory hazard to any crew breathing the interior atmosphere if even a small amount infiltrated. The sulfuric acid cloud layer also has specific effects on the radio communications between a surface mission and any orbiting relay spacecraft. The cloud layer is relatively transparent to X-band and higher frequency radio waves, which are used for spacecraft communications, so this is not a critical problem. but the cloud layer reflects radar extremely efficiently, which is why Venus was the first planet to have its surface mapped by radar from orbit. And this reflectivity contributes to the planet's extreme brightness in the night sky. The cloud layer is also the source of the global wind system that circulates Venus's upper atmosphere. The upper atmosphere, above the clouds, rotates around the planet in approximately 4 days, much faster than the planet's surface rotation rate of 243 days. This super-rotation of the atmosphere is not well understood, but creates the persistent high-altitude wind that a cloud-level habitat would need to accommodate or exploit. The history of human attempts to explore Venus's surface is the history of the Soviet Venera program, and it is one of the most dramatic sagas in the history of space exploration. It is a story of extraordinary engineering achievement and of a planet that destroyed every vehicle sent to its surface within hours, without exception. The Soviet Union launched the first successful Venus probe, Venera 3, in 1965. It was the first spacecraft to impact another planet's surface, but it failed before returning any data. Venera 4, launched in 1967, entered Venus's atmosphere and transmitted data for 93 minutes, as it descended before being crushed by the pressure at about 25 kilometers altitude. Soviet scientists had not correctly anticipated how much denser the atmosphere would be at that altitude compared to their models. Venera 7, launched in 1970, was the first spacecraft to successfully transmit data from the surface of another planet. It survived on the surface of Venus for 23 minutes before the heat and pressure overwhelmed it. 23 minutes. The engineering team was ecstatic. They had reached the surface. They had transmitted data. They had proved it was possible. But 23 minutes is not a long time. Venera 8 survived for 50 minutes in 1972. Venera 9 survived for 53 minutes in 1975 and transmitted the first photographs of Venus's surface, revealing a landscape of jagged rocks and boulders, illuminated by the dim orange light filtering down through the clouds. The images showed a surface that looked young by geological standards, suggesting active geology. Venera 10 also survived for 65 minutes. Venera 13, launched in 1981, reached Venus in 1982 and achieved the record survival time, 127 minutes, 2 hours and 7 minutes. It transmitted color photographs of the surface, analyzed the soil composition, and recorded sounds of the Venusian wind. Then it died, exactly as the physics said it must. Why does every probe die? The answer is heat and pressure. The 465-degree environment outside the probe pumps heat through the probe's thermal insulation at a rate that cannot be indefinitely compensated. The probe's internal temperature rises. At some point, the electronics, typically designed to operate at temperatures up to about 125 degrees Celsius for hardened components, fail. Simultaneously, the 92-bar external pressure is trying to crush the probe's pressure vessel. The seals between components are being attacked by acid vapor. The combination of these factors, operating continuously from the moment of landing, will destroy any probe or spacecraft that is not continuously rejecting heat through active cooling. To maintain human habitable conditions inside a surface habitat on Venus, you would need to reject heat continuously at a rate equal to the heat flowing in through the insulation. At a temperature differential of roughly 440 degrees between the desired interior temperature of approximately 25 degrees Celsius and the exterior 465 degrees, With any practical thickness of thermal insulation, the heat flow inward would be enormous. You would need a refrigeration system of extraordinary capacity, powered by a nuclear reactor, operating continuously without mechanical failure, in an environment that destroys mechanical components through corrosion and thermal stress. If the refrigeration system failed for any reason, the interior of the habitat would reach lethal temperatures within minutes. There is no safe mode. There is no way to pause operations and wait for help. The environment is actively trying to kill everything inside, and it succeeds within hours when the engineering opposition stops. This is why 127 minutes is the record. Not because Soviet engineers were insufficiently clever, not because the probes were poorly built, but because the mathematics of heat rejection in a 465-degree environment are brutal, and the Soviet probes were designed to survive as long as possible, with finite thermal mass, rather than with continuous active cooling. A probe using continuous active cooling powered by a nuclear reactor could survive longer. But 127 minutes represents the limit of what purely passive thermal management can achieve in that environment, and it is a number that puts the challenge in very concrete terms. Let us now confront the suit problem, because this is where the Mars comparison becomes stark. For a Mars surface mission, the engineering challenge of a suit is real but tractable. Mars has a surface pressure of about 0.006 bars and a temperature that ranges from -125 degrees Celsius at the poles in winter to about 20 degrees Celsius at the equator on a warm day. A Mars suit needs to maintain pressure, protect against the cold, filter the atmosphere, and resist the fine abrasive dust. It is a severe engineering challenge, but it is one that existing spacesuit technology, evolved from the suits used on the Moon, is broadly capable of addressing with improvements. A Venus surface suit would need to do something categorically different. It would need to protect the occupant from 92 bars of external pressure, while allowing the wearer to move and work. It would need to insulate against 465 degrees Celsius while rejecting the heat that flows through the insulation into the suit's interior. It would need to resist concentrated sulfuric acid aerosol on its exterior surfaces, and it would need to maintain a breathable interior environment at normal pressure. The pressure requirement alone is disqualifying for a conventional suit. At 92 bars of external pressure, the suit would need to support the full weight of 92 atmospheres, pressing inward on every square centimeter of its surface. The force per square meter at 92 bars is approximately 9.2 million newtons, roughly the thrust of a large rocket engine, pressing inward on every square meter of the suit's surface. The suit would have to resist this force structurally. The joints that allow movement would need to function under this pressure differential. The suit would need to be, effectively, a personal pressure vessel with articulated joints, similar in engineering terms to a submarine with arms and legs. There is no human wearable suit of this type that currently exists, or is close to existing. Deep-sea diving suits used in oil industry operations can withstand a few hundred bars of external pressure, but they are rigid atmospheric diving suits, in which the human inside is effectively sitting in a pressurized capsule, rather than wearing a flexible suit. Movement in such suits is limited and awkward. Work in them is possible, but requires careful engineering of the external manipulators. They are not suits in any normal sense. They are small submarine-like vehicles that happen to be shaped roughly like a human. The temperature requirement compounds the problem. A suit that could withstand 92 bars would need to be constructed of heavy-gauge materials that do not insulate particularly well. Heat flow through a thick metal pressure vessel wall is significant at a 440-degree temperature differential. Active cooling of the suit interior requires power, which requires a power source worn by or attached to the suit, which must also survive at 465 degrees Celsius. Externally, the refrigeration compressors and heat exchangers would need to reject heat into the 465-degree environment, which means the heat exchanger working fluid would need to be at a temperature significantly above 465 degrees in order to reject heat into it. The thermodynamics of this problem are severe. The acid resistance requirement means that the exterior of the suit must be constructed of or coated with materials that resist concentrated sulfuric acid at elevated temperatures. Polytetrafluoroethylene, commonly known by the trade name Teflon, resists sulfuric acid extremely well, but it has a thermal degradation temperature of about 260 degrees Celsius. Above that temperature, it begins to break down. It would not survive long in the Venusian surface environment. High-purity gold and platinum are acid-resistant, but neither is a practical structural material for a pressure suit. What would a Venus surface suit actually look like if engineers tried to build one? It would look like a miniature submarine. It would be essentially rigid. Movement would be limited to simple arm and leg motions, mediated by external manipulators, similar to those used in nuclear handling equipment. The weight of such a suit on Earth would be extreme, likely hundreds of kilograms. On Venus, where gravity is 90.5% of Earth's, the suit would still weigh several hundred kilograms in the Venus gravity field and would be extraordinarily difficult to move in. Any work that required fine manipulation, drilling, sampling, equipment maintenance would be performed through articulated mechanical hands that would transmit only limited tactile feedback to the wearer. The honest assessment from materials scientists and pressure vessel engineers who have analyzed this problem is that a suit allowing meaningful surface work on Venus is not achievable with foreseeable. Materials science and engineering. The individual requirements, high pressure resistance, high temperature resistance, acid resistance, and joint flexibility for mobility, conflict with each other at the combination of pressure and temperature that Venus presents. A suit good enough for one requirement fails at another. There is no material and no engineering approach that satisfies all requirements simultaneously at Venus surface conditions. This means that any crewed surface mission to Venus, even if the vehicle could be engineered to survive, would leave the crew unable to exit the vehicle. They would be observers through windows, not explorers of the surface. Every task that required direct human manipulation would need to be performed through remotely controlled arms attached to the outside of the habitat vehicle. The crew would be, in effect, pilots of a very sophisticated robot that happened to contain them. Whether this constitutes meaningful human exploration of Venus's surface is a philosophical question. But it is clear that it is not exploration in the sense that lunar walks or even Mars surface walks represent exploration. Even setting aside the impossibility of meaningful surface work, let us address the return problem in the way the Mars videos addressed it, through the fuel mathematics. Venus has a surface gravity of 8.87 meters per second squared, compared to Earth's 9.81 meters per second squared. The surface gravity of Venus is 90% of Earth's. This means that escaping from Venus's gravity well requires nearly as much energy as escaping from Earth's gravity well. The escape velocity from Venus's surface is approximately 10.36 kilometers per second. The escape velocity from Earth's surface is 11.19 kilometers per second. They are nearly identical. Compare this to Mars. Mars's escape velocity from its surface is 5.03 kilometers per second, less than half of Venus's. The fuel mass required to achieve a given delta V is not linear with that delta V, but exponential, as described by the Tsiolkovsky rocket equation. This means that the fuel requirement for launching from Venus's surface to orbit is not merely twice that of launching from Mars's surface. It is several times greater, depending on the specific trajectory and the mass of the vehicle being launched. But the gravity situation on Venus is actually worse than the comparison with Earth suggests, because Venus's thick atmosphere must also be penetrated during ascent. Any rocket launching from Venus's surface must push its way through 92 bars of dense CO2 atmosphere. The aerodynamic drag during ascent through the dense lower atmosphere is enormous. A rocket that would reach orbit from Earth using a certain amount of fuel would require significantly more fuel to reach orbit from Venus, because the lower atmosphere of Venus is far denser than Earth's at low altitudes. The drag losses during the initial phase of ascent through Venus's thick lower atmosphere would be substantial. The in-situ resource utilization approach that might make a Mars return mission feasible does not translate to Venus. On Mars, the plan is to use the CO2 atmosphere and water ice from the soil to manufacture methane and oxygen propellant through the Sabatier reaction. This requires extracting water ice from the soil and electrolyzing it to produce hydrogen and oxygen. On Venus, there is no water ice. The surface is too hot for water to exist in any form. The atmosphere contains water vapor at trace levels, parts per million, far too dilute to extract efficiently. There is no hydrogen source on Venus's surface from which to manufacture methane fuel. The only abundant raw material on Venus's surface is CO2 from the atmosphere. CO2 can potentially be converted to carbon monoxide and oxygen through high-temperature electrolysis, and carbon monoxide can be used as a rocket propellant in some configurations. But carbon monoxide is a significantly less efficient propellant than methane, requiring more mass to achieve the same thrust and the same velocity change. And the equipment required to perform high-temperature CO2 electrolysis would need to operate reliably in the 465-degree, 92 bars environment. Every piece of processing equipment that must operate on Venus's surface is subject to the same destruction that claims every spacecraft within hours. The conclusion is stark. There is no credible path to return from Venus's surface. You cannot manufacture sufficient fuel there. You cannot bring sufficient fuel with you. And even if you somehow solved both of those problems, you cannot build a suit that would let you work on the surface long enough to fuel and prepare a return vehicle. Venus's surface is, for all practical engineering purposes, a one-way destination in a more fundamental sense than Mars. Mars is a one-way destination because the economics of return are prohibitive. Venus's surface is a one-way destination because the physics of survival are prohibitive before the economics of return even become relevant. Here is a fact about Venus that almost nobody knows, and that once you understand it, changes how you think about what the surface experience would actually be like. The surface of Venus has never, in its entire history since the runaway greenhouse took hold, seen direct sunlight. The cloud cover is permanent. It is not like Earth's cloud cover, which comes and goes with weather systems and clears in fair weather. Venus has no weather in the sense that Earth does. There are no storms that clear the sky. There are no seasons that change the cloud patterns. The sulfuric acid clouds are produced continuously by volcanic outgassing of sulfur dioxide, which reacts with water vapor and CO2 at altitude to form sulfuric acid droplets, and they are destroyed continuously by downward transport to lower altitudes where the higher temperature causes the droplets to evaporate and the sulfur compounds to react with surface rocks. And the cycle repeats. The global cloud cover is a permanent, continuous feature of Venus's chemistry. It has been there for billions of years. It will be there for billions more. Standing on the surface of Venus, you would never see stars. You would never see the sun. You would never see the moon or Earth. You would see, above you, the orange-yellow glow of the cloud deck, lit from within by the diffuse sunlight penetrating from above. The light level at Venus's surface is roughly similar to an overcast day on Earth, perhaps slightly dimmer. It is not completely dark. The clouds are bright enough to provide useful illumination, but the sky is a uniform orange-yellow dome, with no features, no variation, no sun or stars, no point sources of light anywhere. The horizon is approximately 7.5 kilometers away, similar to Earth's horizon distance, and beyond it, the surface curves away under the orange glow. The surface is covered with rocks. The Venera photographs showed basaltic rocks, similar in composition to the rocks you find at volcanic fields on Earth. The rocks appear to be relatively fresh, not heavily eroded or weathered. This is consistent with the evidence for ongoing or geologically recent volcanism on Venus. The surface is not the ancient, impact-cratered surface of Mars or the Moon. It appears to be relatively young, resurfaced by volcanic activity on geological timescales. The wind on the surface is very gentle. Venus's slow rotation produces very weak surface winds, typically only a few kilometers per hour. This is actually one of the very few aspects of the Venusian surface environment that is less hostile than Mars. Mars has relatively strong surface winds, capable of transporting fine dust and creating global dust storms. Venus's surface winds are calm. This means that surface installations would not face wind loads, and fine dust would not be blown onto surfaces and equipment as it is on Mars. But the gentleness of the surface wind is irrelevant given every other hostile factor. The calm wind is the single positive data point in a list of negatives that would fill several pages. It is like noting that the firing squad has excellent aim. We have established that a human surface mission to Venus faces essentially insurmountable challenges in survival, in suit technology, and in fuel production for return. Let us put numbers to the return fuel problem more precisely, because the comparison to Mars is instructive. A mission returning from Mars's surface needs to achieve Mars orbit, then execute a trans-Earth injection burn to leave Mars's sphere of influence and travel back to Earth, and finally perform an Earth orbit insertion or direct atmospheric entry at Earth. The total delta-V budget for these maneuvers, starting from Mars's surface, is approximately 9 to 10 kilometers per second. This is a substantial fuel requirement, but it is one that mission architects have developed credible plans for, particularly with the ISRU approach of manufacturing methane and oxygen propellant from Martian atmospheric CO2 and subsurface ice. A mission returning from Venus's surface would need to achieve Venus orbit and then execute a trans-Earth injection burn. The delta-V for these maneuvers, starting from Venus's surface, is approximately 13 to 14 kilometers per second. This is 30 to 40% more than the Mars case, and it must be achieved without any ISRU capability on the surface. The entire return fuel load must be brought from Earth at a specific impulse of approximately 370 seconds for methane-oxygen engines. Achieving 13 to 14 kilometers per second of delta V from a starting point of zero velocity on Venus's surface requires a mass ratio of approximately 40 to 1. For every kilogram of payload returned to Earth orbit, roughly 40 kilograms of propellant must be present on Venus's surface at the time of liftoff. If the return vehicle has a mass of, say, 10,000 kilograms, including crew and life support and sample return capsule, it would require approximately 400,000 kilograms of propellant on Venus's surface. 400 metric tons of propellant. This would need to be landed on Venus's surface before the crew arrived. Landing 400 metric tons of liquid propellant on a planet where the surface destroys anything placed on it within hours, where the atmospheric pressure is 92 bars, where the temperature is 465 degrees Celsius, is not a mission scenario that any serious engineering analysis has found feasible. Compare this to the Mars scenario. On Mars, the same return vehicle requires approximately 180,000 to 200,000 kilograms of propellant. And this propellant can be manufactured on the surface from local resources over a period of 18 to 24 months before the crew arrives. The fuel does not need to be landed from Earth. The only hardware that must be landed is the ISRU plant, the power source, and the empty return vehicle, none of which need to maintain propellant at cryogenic temperatures in a 465-degree environment. The Mars return scenario has a clear engineering path. The Venus surface return scenario does not. The conclusion from all of this, the temperature, the pressure, the acid clouds, the suit impossibility, the fuel mathematics, is that landing humans on Venus's surface is not merely extremely difficult. It is, with any technology that can be extrapolated from what currently exists, essentially impossible to accomplish in a way that includes a return trip. Anyone who descended to Venus's surface would be there permanently, not in the heroic, long-term settlement sense of the Mars colonists, but in the much grimmer sense that they could not survive long enough to attempt return, even if the fuel were available. The surface of Venus is not a place where humans could live for years building a colony. It is a place where humans could survive, with our best current technology, for minutes. This is why the second half of this story matters so much. Because despite everything we have described, despite the hellish surface, despite the acid clouds, despite the crushing pressure and the furnace temperature and the searing corrosion, there is a place on Venus where the story is completely different. And it is not a hypothetical future technology. It is a place that exists right now, held in place by the same physics that makes the surface impossible. A band of sky, 50 kilometers above the worst environment in the solar system, where the temperature is moderate, the pressure is familiar, and a human being properly equipped could potentially work and live. That is where part 2 begins. Everything we have described in part 1 is true of Venus's surface, the 465 degrees Celsius, the 92 bars of pressure, the acid clouds, the impossibility of a functioning suit, the complete absence of any viable return fuel chemistry. If you landed on Venus's surface, you would die within minutes, possibly within seconds depending on your vehicle's failure mode, and you would not be coming back. But here is where the story of Venus does something that the story of Mars does not do. Mars has one habitable option: the surface. The surface is hostile, cold, irradiated, and barren, but it is at least physically survivable with the right technology, and returning from it is at least theoretically feasible, with enough fuel. Mars's one option is difficult. Venus's surface has zero options. Zero. But Venus has a second option that Mars does not have. Its sky. 50 kilometers above the surface of Venus, the atmosphere is transformed. Not by imagination, not by future technology, not by any terraforming or modification, simply by altitude. As you ascend through the Venusian atmosphere, every one of the catastrophic factors we described diminishes. The pressure drops. The temperature drops. The acid concentration changes in character. At 50 to 54 kilometers above the surface, something extraordinary happens. The conditions arrive at a band that is, by every metric we use to evaluate planetary habitability for humans, the most Earth-like environment that exists anywhere outside of Earth itself. Let us be specific. At 50 kilometers altitude on Venus, the atmospheric pressure is approximately 1 bar. 1 bar. The pressure at Earth's sea level is 1.013 bars. At 50 kilometers altitude on Venus, the pressure is essentially identical to standing at sea level on Earth. You could survive this pressure without a pressure suit. The crushing weight of 92 atmospheres that would kill you at the surface has, by the time you have ascended 50 kilometers, dropped to a value that your body handles every day without any special equipment. At 50 kilometers altitude on Venus, the temperature is approximately 75 degrees Celsius at the lower end of this altitude band, and drops to approximately 30 degrees Celsius at the upper end, near 54 kilometers. 75 degrees Celsius is hot, about the temperature of very hot bath water. Uncomfortably hot, but not immediately lethal. 30 degrees Celsius is simply a warm day. A properly designed habitat at this altitude, insulated and with modest active temperature management, could maintain a perfectly comfortable interior. This is not the same order of magnitude challenge as managing 465 degrees at the surface. A temperature difference of 40 degrees between inside and outside is trivially manageable with ordinary insulation. We do this in buildings every day on Earth. At 50 kilometers altitude on Venus, the solar irradiance arriving at the habitat is approximately 1,400 watts per square meter, almost exactly the same as the solar constant at Earth's distance from the Sun. Venus receives more solar energy per unit area than Earth because it is closer to the Sun. But at 50 kilometers altitude, a significant fraction has already been absorbed and scattered by the overlying cloud layers. The result is that the solar energy available at the cloud tops is very close to what Earth's surface receives from direct sunlight. Solar panels work at Venus's cloud level. They work very well. At 50 kilometers altitude on Venus, the wind speed is approximately 60 to 100 meters per second. A persistent zonal flow moving from east to west at roughly 360 to 600 kilometers per hour. These winds are not storm systems. They are the permanent, continuous superrotation of Venus's upper atmosphere, which has been flowing in this manner for billions of years. The winds are strong, but consistent. A habitat designed to ride these winds, carried around the planet on the flow, would circle Venus in approximately 4 Earth days at this altitude, traveling eastward relative to the surface. The winds do not vary dramatically in speed or direction. They are as predictable as a trade wind on Earth, and like trade winds, they are a resource as much as a hazard. At 50 kilometers altitude on Venus, radiation levels are lower than on the Martian surface. This fact deserves emphasis because it inverts the intuitive expectation. Venus has no global magnetic field. This should mean high radiation, like Mars. But the 50-bar equivalent column of atmosphere between the cloud level at 50 kilometers and the cloud tops at 70 kilometers provides radiation shielding that is far more effective than the few millibars of atmosphere that Mars provides. The dense atmosphere absorbs and scatters high-energy particles and photons efficiently. The radiation environment at Venus's cloud level is actually more benign than at Mars's surface, where the thin atmosphere and absent magnetic field leave the surface poorly shielded. And here at 50 kilometers altitude on Venus, the atmosphere is composed of approximately 96.5% carbon dioxide. This is the same atmosphere that is so deadly at the surface because of its temperature and pressure. But at cloud level, this chemistry has a remarkable property. A habitat filled with a breathable nitrogen-oxygen atmosphere at a pressure of 1 bar has an average molecular mass of approximately 29 grams per mole. The ambient Venusian atmosphere at 50 kilometers altitude is CO2 and nitrogen with an average molecular mass of approximately 43 grams per mole. The habitat's interior gas is lighter than the surrounding atmosphere. The habitat floats, not through any technological trick, not through helium balloons or heat-generating buoyancy, simply because the gas inside the habitat is inherently lighter than the gas surrounding it. This is the defining insight of the Cloud City concept. On Venus, human habitation naturally floats. A structure sealed against the exterior atmosphere and filled with the air that humans breathe is, by the laws of physics, a lighter-than-air vehicle in the Venusian cloud layer. Buoyancy is free. No lift gas is required. No active lift system is required. A habitat in Venus's cloud layer floats because breathing air is less dense than CO2 at the same pressure and temperature. The very act of making the habitat inhabitable makes it buoyant. This is not a speculative idea proposed by enthusiasts on the internet. It is a formally studied mission concept, developed by engineers at NASA's Langley Research Center and presented at peer-reviewed conferences. Its name is HAVOC, which stands for High Altitude Venus Operational Concept. The lead researchers include Christopher Jones and Dale Arney from Langley, and the concept has been refined through multiple iterations since it was first publicly presented around 2014 and 2015. The HAVOC concept proposes a staged program of Venus exploration that begins with robotic precursor missions and builds toward a crewed mission that spends approximately 30 days in the Venusian atmosphere at an altitude of approximately 50 kilometers. The crewed component involves a habitat deployed in the cloud layer, carried around the planet by the persistent winds, operating as a floating research station. The mission profile works as follows. A crewed transfer vehicle departs Earth and makes a transit to Venus over approximately 3 to 5 months. The crew of 2 to 4 astronauts performs the transit in the transfer vehicle, which has full life support systems and provides a habitable environment during the journey. Upon arrival at Venus, the transfer vehicle enters Venus orbit. A habitat vehicle, previously deployed and tested in an automated configuration, is released from the transfer vehicle and enters the Venusian atmosphere. The habitat vehicle descends through the upper atmosphere. Above 60 kilometers, it is in near vacuum by terrestrial standards. Between 60 and 50 kilometers, it passes through the sulfuric acid cloud layer. The exterior of the habitat is coated with acid-resistant materials, primarily a layer of PTFE-based coatings on the upper surfaces where cloud droplet impingement is most significant, with titanium alloy structural elements. At 54 kilometers, the habitat has descended into the stable float band. An inflatable envelope surrounding the habitat deploys. The envelope contains the habitat's breathing air, providing buoyancy. The entire structure, envelope plus pressurized habitat module, settles into the float altitude band and begins drifting on the zonal wind. The crew then descends from the orbiting transfer vehicle in a smaller entry capsule. This entry capsule is expendable. It is designed for one-way entry into Venus's atmosphere, with no capability for ascent back to orbit. It descends through the clouds and rendezvouses with the floating habitat in the cloud layer, docking with it. The crew transfers into the habitat. The entry capsule is jettisoned. For the next 30 days, the crew lives and works in the floating habitat, drifting at approximately 60 meters per second through the cloud layer, circling Venus every 4 Earth days. At the end of the mission, a return vehicle is launched from the habitat. This is the most technically challenging element of the mission. The return vehicle must ascend from 50 kilometers altitude through the acid cloud layer, through the upper atmosphere, and achieve Venus orbital velocity to rendezvous with the waiting transfer vehicle. The return vehicle is not launching from the surface. It is launching from an already moving platform at 50 kilometers altitude, with 1 bar of pressure surrounding it, and a temperature of approximately 30 to 75 degrees Celsius. The delta V required for this maneuver is significantly less than launching from Venus's surface. From 50 kilometers altitude on Venus, the delta V required to reach Venus orbit is approximately 7 to 8 kilometers per second, compared to 13 to 14 kilometers per second from the surface. This is a significantly more manageable fuel budget. The return vehicle can be sized to accomplish this maneuver with a fuel load that can be brought from Earth as part of the mission. The return vehicle, after achieving Venus orbit, rendezvous with the transfer vehicle, the crew boards, and the transfer vehicle departs for Earth on the next available launch window, approximately 16 months after arrival. The complete Havoc mission architecture fits within a mass budget roughly comparable to a Mars surface mission, in terms of the hardware required. The habitat does not need to withstand surface conditions. It operates in an environment similar in pressure and temperature to Earth. The only exotic engineering requirements are the acid-resistant exterior coatings and the aeroshell protection during atmospheric entry. These are solvable problems with existing or near-term materials science. The mission concept is technically credible. NASA has not formally selected Havoc as a mission to develop. It remains a concept study, but it represents something important: the existence of a viable, physically real engineering path to placing humans in the Venusian atmosphere and bringing them back. The surface is inaccessible. The clouds are habitable. This is the paradox of Venus. Here is a fact that most people have never heard, and that changes how you think about Venus entirely. Venus was almost certainly a habitable world for a significant fraction of its history. Not marginally habitable, genuinely, perhaps comfortably habitable, with liquid oceans, moderate temperatures, and an atmosphere that may have supported the emergence of life, for a period estimated between 1 and 3 billion years. This finding emerged from climate modeling studies in the 2010s, particularly from work published by Michael Way at NASA's Goddard Institute for Space Studies and collaborators at Uppsala University, published in the journal Geophysical Research Letters in 2016. Their simulations modeled Venus's climate for periods when the Sun was younger and cooler, using assumptions about Venus's early rotation rate, topography, and atmospheric composition, and found that under plausible conditions, Venus could have maintained a stable, moderate climate, with surface temperatures in the range of 20 to 50 degrees Celsius and liquid water on its surface. The early Sun was approximately 70% of its current luminosity. At that reduced solar output, a planet at Venus's distance, with an early atmosphere containing modest amounts of CO2 and nitrogen, and with liquid water on its surface, could have been within the habitable zone. The water cycle would have operated: evaporation, cloud formation, precipitation. The carbonate-silicate cycle would have drawn CO2 out of the atmosphere as temperatures rose and released it as temperatures fell, providing a natural thermostat just as it has done for Earth. Venus might have had a fully functional biosphere-friendly climate for roughly 3 billion years. Why did it end? The leading hypothesis is that as the Sun brightened over geological time, Venus approached and eventually crossed the runaway greenhouse threshold. The threshold crossing may have been assisted by a period of intense volcanism that released large amounts of CO2 into the atmosphere, tipping the balance. Or it may have been triggered by a different mechanism, possibly even a large impact event that accelerated volcanic outgassing. The geological record of what triggered Venus's transformation is obscured by the fact that the entire surface appears to have been resurfaced by volcanic activity roughly 300 to 700 million years ago, erasing the older geological record. 3 billion years of potentially habitable conditions. Earth is approximately 4.5 billion years old. Life appears to have emerged on Earth within the first half-billion years, meaning it has had roughly 4 billion years of continuous evolution. If Venus had 3 billion years of habitable conditions, and if the emergence of life is not extraordinarily improbable given the right conditions, then Venus may have had its own biosphere for much of its history. And here is where the story of Venus's habitability becomes even more extraordinary. If life existed on Venus's surface during its habitable period, some of it might still exist, not on the surface, which has been uninhabitable for hundreds of millions of years, in the clouds. The suggestion that life might persist in Venus's clouds is not a fringe idea. It has been seriously considered by astrobiologists since Carl Sagan and Harold Morowitz proposed it in a 1967 paper in Nature. The cloud layer moderate temperature and pressure, making and there is sulfur, water vapor at trace levels, carbon dioxide, and solar energy available. The main challenge is the acid. Concentrated sulfuric acid is lethal to most life as we know it. But extremophile organisms on Earth survive in environments that would kill most other life. Acidophile bacteria on Earth thrive in pH 0 environments. The pH of Venus's cloud droplets is approximately -1.5, more acidic than anything that supports terrestrial life. But the gap is not infinite. Organisms adapted specifically to the Venusian cloud environment might have evolved acid-resistant membranes using entirely different biochemistry from terrestrial life. The clouds of Venus provide conditions where the basic requirements for life, energy, chemistry, and a liquid medium are potentially present. The sulfuric acid droplets are the liquid medium. Solar energy is the energy source. The atmospheric chemistry provides the raw materials for metabolism. If life emerged on Venus's surface when conditions were hospitable, and if some of those organisms were carried aloft into the atmosphere by volcanic eruptions or atmospheric convection, and if some of them adapted over geological time to the increasingly hostile conditions as the surface became uninhabitable, some of them might exist today in the cloud droplets of Venus, surviving in the least extreme environment available on a world that became extreme. In September 2020, a team of astronomers, led by Jane Greaves at Cardiff University, announced the detection of phosphine gas in Venus's atmosphere. Measured by the James Clerk Maxwell Telescope in Hawaii and the ALMA Observatory in Chile. Phosphine, pH3, is a compound of phosphorus and hydrogen. On Earth, phosphine is produced by anaerobic microbial organisms and by industrial processes. It is not produced in significant quantities by any known abiotic atmospheric chemistry. The detection, if real, would imply either a completely unknown abiotic chemical process operating in Venus's atmosphere, or the presence of life. The announcement was extraordinary. It made headlines worldwide. The research team was careful and cautious in their claims. They did not say they had found life. They said they had detected phosphine at a concentration of approximately 20 parts per billion, and that they could not explain this concentration through any known non-biological chemistry. They presented it as an anomaly requiring investigation. The announcement was followed almost immediately by extensive scrutiny. Other scientists reanalyzed the telescope data and found that the signal was weaker than initially reported, possibly in the range of 1 part per billion rather than 20, and possibly consistent with instrumental artifacts or systematic errors in the data calibration. The ALMA data, on reanalysis, was found to have calibration issues that reduced the significance of the phosphine signal. Subsequent observations have not produced a confident redetection at the originally claimed levels. The scientific community's current assessment is that the phosphine detection remains uncertain. The signal in the original data is real in some form, but its magnitude is debated, and its origin is unclear. It is not proof of life. It is not disproof of life. It is an anomaly in the data that might be instrumental noise, might be a real but smaller phosphine signal from unknown abiotic chemistry, or might be a real phosphine signal from biological activity. The current state of the science requires more and better data from Venus before this question can be resolved. What the phosphine episode demonstrates is that Venus's atmosphere is scientifically active in ways that are not fully understood. There are chemical species present, or potentially present, that our models do not predict from known abiotic chemistry. Whether life is the explanation or not, the atmosphere of Venus contains chemical puzzles that require in situ investigation to resolve. Robotic probes can make measurements, but the measurement quality and the range of measurements possible from a crude cloud-level station would far exceed what robotic probes operating on limited battery life and without the ability to adapt their investigations in real time could achieve. A human crew floating in Venus's cloud layer for 30 days would not be merely tourists experiencing an exotic environment. They would be conducting scientific investigations that could potentially resolve one of the most profound questions in biology and astrobiology: whether life has arisen more than once in the solar system. If microbial life exists in Venus's clouds, it would provide, for the first time, evidence that life is not a singular event on Earth, but a general outcome of chemistry given the right conditions. The implications for our understanding of the universe's biological potential would be transformative. Even if no life is found, the chemical and physical characterization of Venus's cloud layer at the level of detail possible with a crewed mission would provide unparalleled insights into the chemistry of atmospheric sulfuric acid. Systems, the dynamics of planetary atmospheres under extreme greenhouse conditions, and the geological and volcanic history of Venus, as recorded in atmospheric trace gases. Venus is not merely a curiosity. It is a laboratory for understanding planetary evolution and for understanding what Earth might become under different circumstances. Having established the extraordinary conditions at 50 kilometers altitude, we need to be honest about what remains challenging at cloud level, because the cloud level is not a paradise. It is simply a place where human presence is physically achievable, which is a very different thing from being easy. The primary challenge at cloud level that does not exist at the surface level of Mars is the sulfuric acid aerosol. At 50 kilometers altitude in Venus's atmosphere, the cloud droplets are approximately 75 to 80% sulfuric acid by weight. Any material exposed to the exterior of a habitat must resist this acid environment over the duration of the mission. 30 days of continuous exposure to warm, concentrated sulfuric acid aerosol is a genuine materials engineering challenge. Several materials are known to resist concentrated sulfuric acid. Polytetrafluoroethylene, PTFE, which is the material behind the trade name Teflon, is highly resistant to concentrated sulfuric acid. It can withstand acid exposure at temperatures up to about 260 degrees Celsius, and the cloud level temperatures of 30 to 75 degrees are well within this range. PTFE can be used as a coating on external structural surfaces and as a sealing material for seams and joints exposed to the acid environment. It is not perfectly resistant indefinitely, but 30-day exposure at these temperatures is well within PTFE's capability. Titanium and its alloys are resistant to concentrated sulfuric acid in many conditions, particularly at lower temperatures. Titanium is a structural metal used extensively in aerospace applications and is relatively lightweight for its strength. The external structural elements of a cloud-level habitat could be constructed from titanium alloys coated with PTFE, where direct acid contact is anticipated. Certain fluoropolymer composites and ceramic materials offer excellent acid resistance and can be fabricated into structural forms. The field of acid-resistant materials is well developed on Earth because sulfuric acid is one of the most widely produced industrial chemicals, and enormous engineering effort has been invested in designing equipment that survives in industrial sulfuric acid environments. The Venus cloud level is not as severe an acid environment as some industrial applications on Earth, which involve pure concentrated acid in liquid form at elevated temperatures and pressures. The Venus cloud droplets are aerosol particles of concentrated but not pure acid at temperatures and pressures within the range of terrestrial industrial experience. The acid challenge at cloud level is real, but it is an engineering problem of a kind that has been solved before. In the context of chemical plant equipment, acid mine drainage treatment systems, and industrial materials handling. It is not in the same category as the surface temperature and pressure challenge, which has no terrestrial analog and which no known materials can address. Acid resistance at cloud-level temperatures requires careful design and appropriate materials selection. Surface survival at 465 degrees Celsius and 92 bars is outside the physical capability of any material we know of to support human life. The other specific challenge at cloud level is the acid interaction with solar panels. Photovoltaic solar cells use semiconductor materials, typically silicon, that are attacked by concentrated sulfuric acid. Any solar panels used at Venus's cloud level need to be protected from direct acid droplet contact. This can be achieved through protective glazing with acid-resistant transparent materials. Sapphire glass, which is aluminum oxide, is resistant to sulfuric acid. PTFE-coated glass substrates are resistant. A solar panel assembly with a protective outer layer of acid-resistant transparent material and sealed edges would be capable of operating in the cloud environment for the duration of a 30-day mission. Longer duration missions, months to years, would require more careful attention to degradation rates and replacement strategies. The wind speed of 60 to 100 meters per second at cloud level creates structural loads on the habitat. The habitat moves with the wind, so relative velocity between the habitat and the surrounding air is low in the horizontal direction. But vertical wind shear and turbulence create loads that must be accommodated. The inflatable envelope providing buoyancy must be designed to handle these dynamic loads without failure. Inflatable aerospace structures have been developed for various applications, and the pressure differential between the interior of the envelope, containing breathable air at 1 bar, and the exterior, CO2 at 1 bar, is modest, making the structural requirements for the envelope more relaxed than for a spacecraft pressure vessel designed for vacuum. The habitat module inside the envelope must be pressurized and habitable. Its structure needs to withstand the differential pressure between its interior at habitable atmospheric conditions and the exterior at 1 bar CO2. This is the same pressure differential as a standard aircraft fuselage, one of the most mature engineering problems in aerospace. Aircraft fuselages are routinely pressurized to maintain cabin altitude while flying at cruising altitude, where exterior pressure is much lower. The Venus cloud-level habitat's pressure requirements are comparable to this well-understood problem. Let us make the experience concrete. You are in the crew. You have spent 4 months in transit from Earth in the transfer vehicle. The transfer vehicle is currently in Venus orbit. Through the viewport, you can see Venus below you, a white-yellow sphere completely covered by its unbroken cloud deck. The clouds glow in the sunlight, brighter than any terrestrial cloud, because they are reflecting nearly 80% of the incoming sunlight from their sulfuric acid surfaces. Venus is the brightest object in Earth's sky after the Sun and Moon, for exactly this reason. You board the entry capsule with 1 crewmate. The other crew members remain in the transfer vehicle in orbit. The entry capsule is a one-way vehicle. It has a heat shield and a descent system. It does not have ascent capability. You are committing to a one-way descent into Venus's atmosphere. You will not be able to return to orbit in this vehicle. If the floating habitat is not there when you arrive, you will die in the clouds. The entry capsule begins its descent. At entry interface, approximately 180 kilometers altitude, the capsule enters the atmosphere and begins experiencing aerodynamic heating. The heat shield glows. For several minutes, the G-forces are significant as the dense atmosphere decelerates the capsule from orbital velocity. Below 90 kilometers, the heating diminishes. The capsule is now supersonic, descending through the upper Venusian atmosphere, still above the cloud deck. At 70 kilometers altitude, you enter the top of the cloud layer. The view through the small windows changes from the black of space and the white reflection of the cloud tops to a progressively more orange and diffuse glow as the cloud droplets scatter the light. You are in the acid clouds. The exterior of the capsule is exposed to sulfuric acid aerosol for the first time. The acid-resistant coatings on the exterior are doing their job. The descent through the cloud layer takes approximately 30 minutes. During this time, you are descending through progressively denser regions of the cloud. The ambient pressure increases from near vacuum at 70 kilometers to approximately half a bar at 55 kilometers. The temperature increases from the cold of the upper atmosphere, minus 60 degrees Celsius at 70 kilometers, to the warmer cloud layer, temperatures approaching 60 degrees Celsius at 55 kilometers. The capsule's heat rejection systems manage this temperature transition. At 54 kilometers, you break through the bottom of the cloud layer into clear air. The view changes dramatically. Above you, the cloud deck is a uniform yellow-orange ceiling, uniformly bright, extending in every direction. Below you, the atmosphere clears progressively. The light is softer, diffuse, filtered through the overlying clouds. In the distance, perhaps 10 to 15 kilometers away, you can see the floating habitat, a silver-gray ovoid shape drifting on the wind, its inflatable envelope catching the diffuse sunlight. The rendezvous system in the capsule has been tracking the habitat throughout the descent. The capsule maneuvers on small thrusters to match the habitat's velocity. In a dense atmosphere, maneuvering is easier than in vacuum, because aerodynamic surfaces work. Fins and control surfaces respond to the airflow, and the capsule can be steered toward the target with relatively modest propellant expenditure. After several minutes of approach, the capsule docks with the habitat. You hear the docking mechanism engage through the hull. The pressure equalizes between the capsule and the habitat. You open the hatch. You enter the habitat. The habitat interior is approximately the size of a large recreational vehicle, perhaps 12 meters long and 3 meters in diameter. It has workstations, sleeping quarters, a galley, life support equipment, storage for scientific instruments and sample containers, and viewports. The viewports look out into the orange-lit sky of Venus's cloud layer. Through them, you can occasionally see the cloud deck above, and, in clear periods, the hazy distance below where the atmosphere thickens toward the invisible surface, still 49 kilometers down. The wind carries you at approximately 70 meters per second. In 4 Earth days, you will have circled Venus once. In 30 Earth days, you will have circled Venus approximately 7 times, covering a total path length of roughly 270,000 kilometers. You will have traveled a distance greater than the distance from Earth to the Moon, while floating in the atmosphere of another planet. The outside temperature at your float altitude varies slightly with latitude and time of day. At noon on the Venusian day side, the temperature may be slightly warmer. At the terminator, the boundary between day and night, conditions may be slightly cooler. The persistent wind keeps conditions relatively uniform. You are not experiencing weather in any dynamic sense. You are drifting in a river of air that flows on a timescale of 4 days, circling a planet that takes 116 days to turn. Every day, you perform scientific observations. You deploy instruments into the exterior of the habitat that sample the cloud droplets directly and analyze their chemical composition. You observe the cloud layer in multiple wavelengths. You listen to the electromagnetic environment of Venus, checking for radio emissions that might indicate lightning, which has been suggested but not definitively confirmed on Venus. You analyze trace gases in the atmosphere at your altitude, looking for the phosphine signature and for other chemical anomalies. You monitor pressure and temperature profiles. You observe the surface through radar instruments. If a radar system is included in the habitat's scientific package, the return approach is something you think about every day. The return vehicle is attached to the habitat. It has been pre-fueled with propellant that was brought from Earth. In 30 days, you will board it, detach from the habitat, and begin ascent. The return vehicle will climb through the cloud layer, accelerating as the atmospheric density drops. Using aerodynamic lift surfaces in the lower atmosphere and rocket engines in the thinner upper atmosphere, until it achieves Venus orbital velocity and rendezvous with the transfer vehicle waiting in orbit. Then the long journey home begins. The scientific and engineering case for a Venus mission is real and compelling. But the reason the concept has captured serious attention, and the reason it belongs in this conversation about why going to Venus means not coming back, involves something more fundamental than the logistics of mission architecture, or even the search for life. Venus is Earth's warning label. It formed from the same material as Earth, at approximately the same time, at nearly the same distance from the same star, with nearly the same mass, nearly the same composition, nearly the same initial inventory of volatiles, including water and carbon dioxide. For billions of years, it may have been livable. And then it changed. The mechanism of change, the runaway greenhouse effect, driven by CO2 accumulation, is not a Venus-specific exotic phenomenon. It is a physical process that operates on any rocky planet, with an atmosphere and an inventory of CO2. The reason it happened on Venus, and not on Earth, is partly orbital, Venus being slightly closer to the Sun, and partly contingent, dependent on the specific history of volcanic activity and atmospheric evolution on each planet. It is not impossible for it to happen on Earth. In the far future, as the Sun brightens over billions of years, Earth faces the same fate Venus has already encountered. But the timescale for the solar brightening to trigger a runaway greenhouse on Earth is measured in hundreds of millions to a billion years, far beyond any practical near-term concern. The more immediately relevant point is that the same feedback mechanism, CO2 warming, water vapor amplification, more warming, is the foundation of anthropogenic climate change on Earth today. The Venus case study is not a perfect analog, because the concentrations involved are vastly different. Earth's atmosphere has 0.04% CO2. Venus's has 96.5%. The near-term human emissions are not going to push Earth to Venus-like conditions on any human timescale. But Venus shows, in the most vivid possible terms, the end point of a greenhouse runaway on a rocky planet. It shows what happens when the feedback loops operate without restraint. It shows the outcome: a world that may have had oceans, and perhaps life, for 3 billion years, transformed into a place where the rocks melt and the rain is sulfuric acid, and everything we would recognize as habitable has been destroyed for hundreds of millions of years. This transformation is permanent. There is no natural process that will restore Venus to habitability on any timescale relevant to the universe's remaining stellar era. Understanding exactly how Venus crossed the threshold from habitable to hellish is one of the most important scientific questions we can ask. Not merely because it is interesting, but because it has direct implications for understanding planetary habitability more broadly, and for understanding the limits of the habitable zone around stars. Every planet, around every star where life might exist, faces some version of the same questions Venus poses. Did it avoid the runaway greenhouse? Does it currently face it? At what concentration of CO2 does the feedback become uncontrollable? What was the trigger in Venus's case? Was it solely solar brightening, or was volcanic activity a critical accelerant? Was there a point at which a different outcome was still possible? These questions cannot be fully answered from robotic probes that survive for hours or days in the Venusian environment. They require the kind of sustained, adaptive, intelligent investigation that only human presence can provide. A crew floating in Venus's clouds for 30 days, operating sophisticated instruments, responding to unexpected findings in real time, directing the investigation based on what they find, could produce more useful data on these questions than a decade of robotic missions. Not because humans are inherently better than robots as scientific instruments, but because the specific questions posed by Venus require exactly the kind of flexible, adaptive, contextual investigation that humans excel at. This is the scientific justification for accepting the risk and cost of a Venus cloud mission. And the risk is real. The crew going to Venus is going somewhere from which return is possible but not simple. Somewhere that the history of every probe sent there confirms will be actively hostile to their hardware. Somewhere that requires a long outbound journey, a long time in an exotic and dangerous environment, and a technically demanding ascent and return. They know all of this when they go. They are going anyway, if we build the mission and if we find the people willing to go, because the answers that Venus holds are too important not to seek. Other, because it has no good solution and simply must be accepted as a fact of the orbital geometry. Every 584 days, approximately 19 months, Venus passes between Earth and the Sun in a configuration called inferior conjunction. During this transit, Venus is on the same side of the Sun as Earth, moving roughly between us and the Sun. For a period of roughly 2 to 4 weeks around inferior conjunction, the Sun's corona, the outer atmosphere of the Sun, lies between Earth and Venus. The intense radio frequency emission and plasma noise from the corona disrupts electromagnetic communications between the two planets. For this period, reliable radio communication between Earth and any asset at Venus, whether a spacecraft in Venus orbit, a probe in Venus's atmosphere, or a crew in a floating habitat, is impossible. This is not a problem of transmission power or antenna design. No transmitter powerful enough and no receiver sensitive enough can operate through the Sun's corona when Venus is at inferior conjunction. The Sun's radio emission overwhelms any signal from a spacecraft, even the largest and most powerful transmitters that can be placed in orbit. There is no engineering solution. The Sun's noise is physically louder than any signal we can produce. For a robotic mission, communications blackout periods are managed by storing observations and commands and executing pre-planned autonomous operations during the blackout. The Mars rovers and landers routinely operate autonomously for short periods. A blackout of 2 to 4 weeks is longer than any routine communications gap in Mars mission operations, but is manageable in principle by uploading very detailed contingency plans before the blackout begins. For a crewed mission, a communications blackout of 2 to 4 weeks is something different. It means the crew has no contact with Earth, no mission control support, no medical advice from Earth-based physicians, no psychological support from family or counselors, no news from Earth, no emergency assistance. Nothing. They are on their own. If an emergency occurs during the blackout, whether a medical emergency, an equipment failure, an unexpected atmospheric event, the crew must handle it entirely with their own resources and their own training. Earth cannot help. Earth cannot even know what is happening. The Mars missions also face communication delays of up to 44 minutes for a signal to travel one way, meaning any exchange requires almost 90 minutes minimum round trip. But they do not face complete communication blackouts for weeks at a time. When Mars is in solar conjunction, its own communications are disrupted. But solar conjunction for Mars is a shorter and less frequent occurrence than Venus's inferior conjunction. And Mars missions are designed with enough autonomous capability to handle this period. Venus's inferior conjunction is both more frequent and more extended in the disruption it causes to mission operations. The psychological implications of a complete 2 to 4 week communications blackout are significant. The crews of Apollo missions were out of radio contact for roughly 45 minutes each time they passed behind the Moon, which was profoundly stressful for mission control, even for these brief periods. A 2 to 4 week blackout represents a categorically different challenge. The crew must be psychologically robust enough to operate in complete isolation, without contact with Earth or with any other human beings outside the habitat, while conducting a technically demanding mission in a hostile environment for a period of weeks. This is a screening and training requirement that goes beyond the already extreme requirements for deep space mission crew selection. The crew must also be technically capable enough to diagnose and repair any failure that occurs during the blackout period without outside support. Every major system in the habitat must have a human-readable maintenance manual. Every spare part must be pre-positioned, and the crew must have received training sufficient to address any credible failure scenario independently. The mission must be designed on the assumption that any emergency requiring Earth consultation will not receive Earth consultation in time to matter. This is more demanding self-sufficiency than even a Mars mission requires. Who would volunteer for a mission like this? A multi-month transit to Venus, 30 days floating in acid clouds above a world where stepping outside the habitat means certain rapid death, a possible weeks-long complete communications blackout, a technically demanding ascent back to orbit, and a multi-month return transit. And knowledge, full and certain knowledge, that every aspect of the mission, from the 30-day float altitude to the acid-coated exterior of the habitat, to the chemistry of every breath they take in the recycled air, is one engineering failure away from termination. The honest answer is that the people who would volunteer for this mission are the same category of person who has always volunteered to go somewhere most people would not go, and do something most people would not do. They are the same category as the first humans who crossed the Atlantic in wooden sailing ships without knowing if there was land on the other side. The same category as the Antarctic explorers who spent winters in darkness and cold 200 years ago, with equipment and survival resources that would horrify any modern safety engineer. The same category as the first Apollo crews who rode rockets that had failed on previous unmanned tests. They are people for whom the cost of not doing something is greater than the cost of the risks of doing it. Not because they are reckless or cavalier about risk, but because they have calculated, in their own terms, that the value of what the mission accomplishes outweighs what it asks of them personally. Some of them will be motivated primarily by the scientific opportunity, the chance to investigate whether life exists on Venus, to characterize the chemistry of a planet that may tell us the fate of Earth's own atmospheric future, to do science that no robotic system could do as well. These are motivations that scientists find compelling enough to accept extraordinary personal risk. History shows this. Some will be motivated by something harder to articulate. the same thing that motivated the first humans to climb every mountain and cross every ocean. The need to see what is there and to be the person who went there first. This is not vanity. It is a quality of human nature that has driven exploration and discovery since before recorded history, and it is no less real for being difficult to express in cost-benefit terms. Some will be motivated by what they see when they look at Venus from Earth's sky. The brightest star that is not a star, shining in the west at sunset or the east at sunrise. A world that looks in the telescope like a perfect glowing crescent or sphere, beautiful and blank and deeply mysterious, hiding everything about its nature behind its unbroken clouds. There is something about a world that hides itself completely, that compels the people who feel compelled to go into the unexplored. The selection process for such a crew would be extraordinary in its stringency. Not because of the personal qualities needed to survive the mission, though those are severe, but because the crew, during the blackout period and during any emergency, is the only competent authority available. Each crew member must be capable of performing every critical task the mission requires. The medical officer must also be a qualified engineer for habitat systems. The pilot must also be a qualified scientist. The scientist must also be a qualified physician. The redundancy of human capability within the crew is the only redundancy available when the crew is 2 to 4 weeks away from any external support. The psychological screening would be at least as demanding as the technical screening. The ability to function under extreme stress, in conditions of isolation, with incomplete information, against a deadline, with lives depending on decisions made without recourse to external advice, is not a universal human quality. It can be trained and developed, but the baseline must be there. The people selected for the first Venus cloud mission would represent the intersection of exceptional technical competence, extraordinary physical and psychological resilience, and a specific temperament that finds in that intersection not a burden, but a purpose. They would not be coming back soon. They would be gone for well over a year, probably closer to 2 years, accounting for transit times and the mission duration. During the blackout, no one on Earth would know if they were alive. After the mission, they would return to Earth having experienced something that no human had experienced before, and that almost no human would be able to fully imagine based on any analog. The experience of floating in the clouds of Venus, of breathing air inside a structure drifting at 70 meters per second through an acid sky above a world of molten rock, of watching Venus's sun rise in the west and set in the east through the orange glow of the clouds, of knowing that 100 meters below you the pressure would crush any vehicle ever built, and 50 kilometers below you the rocks are hot enough to melt lead, is an experience with no precedent in human history. Let us spend time with what the mission would actually do scientifically, because the science case is ultimately why the mission matters, and why it is worth the risk. The first and most critical scientific objective is the characterization of Venus's cloud chemistry in a level of detail impossible from orbital observations or from probes that survive for hours. The cloud layer is not chemically uniform. There are variations with altitude, with latitude, with the day-night cycle, and possibly with the volcanic activity below. A 30-day mission drifting through the cloud layer would sample a vast range of conditions. Direct sampling of cloud droplets and analysis of their composition using onboard mass spectrometry and other analytical instruments would characterize the sulfuric acid concentration profiles, the trace gas composition including the phosphine question, the organic chemistry, if any, is present, and the particle size and morphology of the cloud aerosols. The second critical objective is the search for life. If life exists in Venus's clouds, it would likely be detectable as anomalous organic chemistry, as cellular structures under microscopy, as metabolic products such as phosphine or other biogenic gases, or as some combination of these. The mission would include high-resolution microscopy capable of imaging individual cloud droplets and searching for cell-like structures. It would include mass spectrometry capable of identifying organic molecules and their isotopic ratios. Since biological systems preferentially process specific isotopes in patterns that distinguish them from abiotic chemistry. It would include real-time analysis capability so that if an anomalous finding was made in one droplet sample, follow-up analysis could be conducted immediately, something a robotic probe cannot do. The third major scientific objective is the characterization of Venus's atmospheric dynamics. The superrotation of Venus's atmosphere, the way the entire atmosphere circulates around the planet in 4 days, while the planet itself turns in 243 days, is one of the most poorly understood phenomena in planetary science. The mechanisms driving it, the energy balance that maintains it, the ways it interacts with the lower atmosphere and the surface are not fully characterized even after decades of orbital observations. A crew embedded in the atmosphere at float altitude for 30 days, with instruments capable of making continuous atmospheric measurements, could characterize the dynamics of the superrotation in unprecedented detail, including its variations with latitude and the day-night cycle and its response to any volcanic outgassing events from below. The fourth objective is the characterization of volcanic activity. Venus is believed to be geologically active, with ongoing or geologically very recent volcanism. The atmospheric chemistry reflects volcanic outgassing. Sulfur dioxide concentrations, measured since the Venera missions, vary over time in ways that suggest active volcanism. A crewed mission with radar and infrared imaging capability could monitor the surface for volcanic hotspots and attempt to correlate atmospheric chemistry changes with specific volcanic events. Catching a volcanic eruption in progress and characterizing the atmospheric response would be an extraordinary scientific achievement that would require sustained monitoring over weeks. Exactly what a crewed mission can provide, and what robotic probes cannot. The broader outcome of all this science is knowledge about how rocky planets evolve. Knowledge directly applicable to understanding Earth's future. Knowledge about the prevalence of life in the universe. And knowledge about the processes that determine whether any given world is or is not habitable. These are not narrow specialist questions. They are questions about our place in the universe and about the future of our own world. NASA's commitment to Venus in the near term is represented by 2 missions selected in June 2021 as part of the Discovery program. Da Vinci I+, for deep atmosphere Venus investigation of noble gases, chemistry and imaging, is an atmospheric probe mission that will descend through Venus's atmosphere while making detailed chemical measurements, surviving for approximately 1 hour below the clouds before impact. It is designed to characterize the noble gas composition of the deep atmosphere, which will constrain the history of Venus's atmospheric evolution and the timing of its transformation from a habitable world. Da Vinci Plus is expected to launch in the early 2030s. Veritas, for Venus emissivity, radio science, INSAR, topography, and spectroscopy, is an orbital mapper that will produce high-resolution radar topographic maps of Venus's surface comparable to what we have for Earth, and will use infrared spectroscopy to characterize the surface mineralogy. Veritas will tell us what Venus's surface is made of, where there has been recent volcanic activity, and what the topographic structure of the planet looks like, at a level of detail that will transform our understanding of Venusian geology. Veritas is also expected to launch in the early 2030s. The European Space Agency has its own mission, Envision, a Venus orbiter with synthetic aperture radar and spectrometer instruments. Expected to launch in the early 2030s in coordination with the NASA missions. The coordinated suite of Da Vinci I+, Veritas, and Envision will provide a dramatically improved picture of Venus over the following decade, addressing many of the questions that currently motivate the argument for a crewed mission. The data from these missions will drive the scientific case for a crewed cloud-level mission. If Da Vinci Plus measures anomalous chemistry in the deep atmosphere consistent with biological activity, the case for a crewed follow-up becomes compelling. If Veritas identifies recent volcanic features suggesting ongoing geological activity, the case for a crewed mission to characterize the atmospheric response becomes stronger. The 2030s will be a decade of intense robotic Venus exploration. The 2040s and 2050s are the realistic window for the development and execution of a crewed Venus atmospheric mission. This assumes sustained investment in both the robotic precursor program and the human spaceflight infrastructure needed for a mission of this complexity. Currently, no space agency has a formal program to develop a crewed Venus mission. The Havoc concept exists as a study. The science case is made in academic papers and conference presentations. The technology development needed for acid-resistant habitat materials, for the return vehicle ascending from 50 kilometers altitude, for the communications protocols during the blackout period. None of this has entered formal development. What it would take to move from concept to mission is what it always takes. A combination of scientific discovery that creates urgency, political will that sustains the investment over the decade-scale development timeline, and engineers and scientists willing to spend careers on a mission whose success they may or may not live to see. These conditions have been met before. They were met for Apollo. They were met for the Hubble Space Telescope. They can be met again. Tonight we trace the entire arc of why going to Venus means not coming back. From the basic orbital numbers that make Venus seem approachable to the surface conditions that make landing on it a death sentence faster than anything in the solar system short of the sun itself. We numbered the acid clouds and the crushing pressure and the blazing heat and the impossibility of any suit that could protect a human, and the futility of any fuel strategy that could lift a crew from the surface back to space. And then we climbed 50 kilometers above all of that, into a band of sky that the same physics that makes the surface impossible has made, by the accident of density and temperature and the behavior of gas in gravity, the most Earth-like place outside of Earth, where the pressure is 1 bar and the temperature is moderate, and the sunlight is adequate, and a structure full of breathing air floats without any technological assistance, held up simply because the gas inside it is lighter than the gas around it. The people who would go to that floating place above the acid clouds are going somewhere they will not be able to leave quickly if something goes wrong. They are going somewhere that every instrument and surface will be continuously attacked by a chemistry that corrodes metal and dissolves organic tissue. They are going somewhere that will be completely cut off from Earth for weeks at a time, with no communication, no support, no possibility of rescue. They are going somewhere that a single critical failure in life support or habitat structure or return vehicle could prevent them from ever coming home. And they are going anyway, if we choose to build the mission, and if we find the people who will choose to go, Because of what Venus holds. Venus holds the answer to whether life arose on a second world in the solar system. If it did, the implications extend far beyond Venus. They imply that life is not a singular accident on Earth, but a general tendency of chemistry given the right conditions. That the universe is likely full of life at various stages of development. That we are not alone in the profound sense of being the only experiment of this kind ever run. If life exists in Venus's clouds, it has been there for hundreds of millions of years, surviving the transformation of the world below it from a habitable ocean planet to a furnace, adapting to the acid environment, persisting in the only habitable zone left on a world that lost its habitability. The resilience and adaptability of life that this would represent is itself a profound fact about the universe. Venus holds the story of how a world goes wrong, of how the habitable becomes uninhabitable, of how the feedback loops that sustain life can be overwhelmed and reversed, of how a planet very similar to Earth, formed in the same stellar nursery, made of the same materials, with the same initial chemistry, can become its opposite. Understanding this story in full requires being in Venus's atmosphere, not merely observing it from a distance. The data that would resolve the uncertainties in Venus's climate history is in the cloud chemistry, and the trace gas profiles and the isotopic ratios of noble gases in the deep atmosphere. And acquiring it requires sending instruments that can sample directly and adapt their sampling based on what they find. Venus also holds a mirror to Earth's future. Not its immediate future, not a future relevant to any timescale of human civilization. But the end point of a planetary greenhouse is visible on Venus today, operating at maximum intensity, having run its full course. A civilization on Venus, if one ever existed during its habitable period, would have had approximately 3 billion years before conditions became untenable, roughly the same total duration as the history of complex life on Earth. If they had our knowledge and our capability and had chosen to leave before the end, where would they have gone? What would they have done with the warning their world gave them? These are not merely rhetorical questions. They are questions about what it means to be a technological civilization on a world with a finite habitable period. We are on such a world. Earth's habitable period extends for hundreds of millions of years into the future, by the most conservative estimates. But it is finite. The sun is brightening. The habitable zone is moving outward. At some point, the same runaway greenhouse mechanism that claimed Venus will claim Earth. Understanding precisely how it happened on Venus, what the trigger was, what the warning signs were, how rapidly the change occurred once it began, is knowledge with direct relevance to our long-term survival as a species. The people who would drift through Venus's acid clouds for 30 days are not merely adventurers. They are not merely scientists. They are emissaries sent to the closest mirror of Earth's possible future, charged with reading in that mirror whatever warnings and knowledge it contains. They will not come back quickly. The mission will last nearly 2 years from departure to return. During the blackout period, no one on Earth will know if they are alive. Every day they are in the clouds. They are one failure away from never coming home. But they will have gone to a place no human has gone. And they will have asked questions that no instrument less capable than a human mind can fully ask. And they will have looked down from their floating island above the clouds at a world that was once perhaps blue and alive, and is now the color of rust and fire and sulfur. And they will have tried to understand how that happened. Because understanding how that happened, in full, is something the universe has given us exactly one clear example of. One world transformed from possibility to impossibility. One mirror of what we must not become. That is why you would go to Venus, knowing you might not come back. Not because you do not value coming back, but because what you might find in those clouds, floating above the most hostile surface in the solar system, is more important than the safety of staying away. That is not just exploration. That is everything exploration has ever been.